that the ligand has to be tightly bound to the receptor. So, well, we use that, and we performed the same simulation that Wu and Ru did, but a longer simulation with a different force field. We used amber, he used charm. We calculated MMPBSA, MMGBSA, and MMGBSA with minimization for 5 different phosphotetrapeptides. The results we got were pretty much in line with what he got. So we said, well, let's take 1,000 snapshots from each simulation and try to do a QM calculation. So we minimized each snapshot, and we calculated the energy with QM using a semi-empirical Hamiltonian PM3 and a continuum solvation model. Of course, it can be objected that if you take snapshots from an MND simulation and you do a minimization, you might lose the constant temperature property. But the minimization was just to relax the system. It was not extensive, because if you go with a semi-empirical method to for long minimization, you begin distorting the system. As you see in the second to last column, the results are impressive when you compare to the experimental values. So that's taking into account entropy. Also, entropy was taken into account as, well, the internal entropy was calculated using a harmonic normal modes and under a harmonic oscillator approach. I can give you the details, I mean, privately, but really the results were quite good. So we are now in line with the experimental results. If you see here the second citation, that was also a paper we just published. It was after this LCK, using also the study of a phosphopeptide binding to another protein, which is BRCT. The results were quite similar to this. I'm going to skip, obviously, the charge transfer part. Basically, in the charge transfer, what we did is a genuine, true QM molecular dynamics simulation on a solvated system of more than 10,000 atoms. This is not Carparinello. Carparinello, it's a very accurate simulation, but right now is just for a more limited system. This is a MD simulation using a semi-empirical method. And our goal was basically to study charge transfer in ubiquity. Conclusions. So the QM-based endpoint method was a step forward in calculating binding free energy, and especially in heavily charged systems. That was also in line with others found, for example, for small molecule binding to other proteins. Well, I haven't shown the slides on charge transfer, but QM was also a good tool. I mean, a QM-MD was a good tool to study and to incorporate charge flow effects in biomolecular systems. And we observed in that case that even though ubiquitin is a neutral protein, there was a significant charge transfer, or I mean, a variable charge transfer from the protein to water. Well, okay, you missed the bonus, but thank you very much, and I'm open to questions.
We have 1 minute. Yes, there, over there.
Thanks, impressive work. One question concerning the last part. If you use semi-empirical quantum mechanic methods to calculate free energies of solvated amino acids, so the solvation free energy of amino acids, it typically comes out that the results are less accurate and deviate more from experimental values than if you use the standard force fields like OPLS or CHARM or so. How would you explain that in your case it's just the other way around?
It would be easy to say that the solution for the problem with MMPBSA, for example, was just a problem of charge transfer. But that's not the case. If you do a classical mechanics calculation of the same system, but not an MMPBSA, a fully solvated using, for example, potential of mean force, you get good results. So the problem there, we are not sure, but we think that the problem with MMPBSA is that classical methods cannot manage properly intrinsic solvation. So a solvation represented by a dielectric. In that sense, QM represents better that. The radii for the atoms, I mean, to calculate solvation energy, which was calculated with Cosmo, they were, in this case, they were optimized with a set of molecules. Later on, we did a more extensive optimization of parameters for a set of about 500 molecules to calculate hydration free energy, and our results were pretty in line with what you say. I mean, we are in 0.6, 0.7 kcal per mole average.
Okay, thank you.